this is the circle we just sketched. So you see again, so this is the same drawing which we did. So this is the general equation of the circle, which is centered as sigma average and tau x prime y prime, right? So here your positive tau is pointing towards the right. So this is the positive direction that I have, right? And here the positive direction for tau is pointing towards downward. So different books follow different convention. This is the easiest one to follow. Now this was the Mohr circle centered as sigma x plus sigma y divided by 2. Any general point P, do not confuse this with anything. This is just a point which I have put over there, for which I am just showing a general stress, general shear stress tau x y, and this is sigma x minus sigma y divided by 2. And also in addition to that, we did a couple of realizations that your maximum principal stresses or maximum and the minimum principal stresses are the extreme ends of the circle, and the extreme top and the extreme bottom are the the absolute maximums of your shear, where also the average stress that you see is the sigma x plus sigma y divided by 2 over here. Okay, now let's take the Mohr circle and see that how it helps in the stress transformation and so on. Now if you take the Mohr circle, so each point of the Mohr circle, as you can see, that represents the two stress components, sigma x prime and the tau x prime y prime. Now although I have indicated this is a general sigma and a general tau, if you look at the basic equation, so this is actually every point is a representation of your sigma x prime and your tau x prime y prime that you have over here, right, acting on the side of an element defined by the x prime axis. Why x prime axis? Because this is sigma x prime. So essentially this is any point within the circle. If you have an element, say rotated about any angle, if you start with the initial point, and which is maybe at any particular angle that is there, and for that you remember that you have the x prime axis, which is inscribing that angle theta over there. So this represents this sigma x prime, which is acting along the x prime axis, and the tau x prime y prime that you have over here. Now remember that is the x prime axis can be anywhere. When your theta is 0 over here, the point where theta is 0, x prime coincides with x, sigma x prime coincides with sigma x. Very simple, right? Now when x prime rotates by say the complete 90 degrees over there, sigma x prime becomes equals to your sigma y in the original one. We will take a look at that one as well. So what I essentially want you to understand is that this x prime axis, it is free to rotate, and as it rotates you will move at different points along the Mohr circle that is there. Let's go ahead and take a look. So first we will start with the very simple case that where your x prime axis is coincident with the x axis. So you see over here theta equals to 0. If you're not able to understand, let me go back to the previous page again. See, this is the theta, where is the x prime was inclined at an angle theta. When theta equals to 0, x prime coincides with the x axis that is there, which is over here. So when you have the x prime coinciding with the x axis, essentially theta equals to 0. So in that particular case, you see that your this particular expression over here, that is your sigma x prime becomes equals to sigma x. You have no option, so you are not rotated anything, you have just kept your element static. So sigma x prime equals to sigma x, and also your tau x prime y prime stays as equal to tau xy over here. Okay, so now let's come to this circle which is over here. Now this circle has many things. Now let's go ahead step by step. Okay, so let's say that this state of stress that is there, for which, and this is again remember a positive element. Why? Because your sigmas are all pointing outwards tensile, and all the taus are either generating in the positive phase and pointing towards the positive direction, or generating in the negative phase and pointing towards the negative direction. So all the state of stress is positive over here. Now if for this state of stress that I have, if I want to represent this point on the Mohr circle, how do I represent that? Now remember, the Mohr circle is actually very simple. The Mohr circle essentially tells you that your horizontal axis is the stress axis, or more particularly it is the sigma x prime axis. So if you make a note of that, so that is the sigma x prime, right? And your vertical axis is the tau axis, or maybe a bit more correctly, that is the tau x prime y prime axis that you have over here. So you see that in this element, where your sigma x prime equals to sigma x, and we have a tau x prime y prime or tau x y. Now within a 2D plane, how many points do you need, or how many values do you need to get a particular point? You need two values. You need a value of sigma x prime, you need a value of tau x prime y prime. So if I have the value of sigma x prime here, which is equals to sigma x, a value of tau x prime y prime that is equals to tau xy. So essentially, if I have this value over here and this value over here, I can put a dot on this Mohr circle that is there, which is shown as this particular point A over here. So if you see this particular point A, here in this particular case, your sigma x prime has become equals to sigma x. Why? Because your general axis is sigma x prime over here. So at this point A, say this is some value, and so this is just shown in terms of variables, but for some particular value, you have your, for this point A, you have come your sigma x prime has become equals to sigma x, and your tau x prime y prime has become equals to tau xy. So you only needed 2 points to put a dot on that particular circle. So this is what it is. So this is essentially your tau, oh sorry, let me erase that. So here you have tau x prime y prime has becomes equals to your tau xy over here, right? So now that you have these 2 points, you can put a dot on that particular circle, which is your point A. So point A was the case where your, so let me maybe write this as A over here, was the case in which your x prime was making just an angle 0 over here. So I have put this particular point over here. Okay, so now let's forget about whatever is remaining. Some of the things you're familiar with. This is the sigma average, where that is where your circle is centered. So let's go and look at the other points which are in this diagram over here. So now I hope you have understood that how we got the point A, which is the original element that you started with over here. And so we got the point A. Now the question is that where, so I know that here I have located my sigma x and the tau xy over here. Now the question is that where in this circle, see in the original element I have 3 things. I have sigma x, sigma y and tau xy. I have located the first and the third, the sigma x and the tau xy. So what happens to the sigma y, right? So how will we get sigma y? Yes, you are right. If I take this x prime axis, which here was at theta equals to 0, and if I rotate it to 90 degrees, then my sigma x prime becomes coincidental with my sigma y prime. So if I rotate that element by 90 degrees over here, I will get a value of the sigma y prime that is there. So let's go ahead and take a look at that one. So you see over here, what is done is that your x prime is rotated by theta equals to 90 degrees. So previously x prime was coincidental with this, now x prime is coincidental with this axis over here. So automatically your sigma x prime becomes equals to sigma y over here. So now in this case, you have your sigma x prime becomes equals to sigma y over here, right? Now one important thing to note in this particular case, what happens to my tau x prime y prime? So you see, now once you have rotated the x prime axis by theta equals to 90, this is your x prime and this is your y prime axis over here. Tau x prime y prime now originates on the positive phase because the outward normal points towards the positive x-axis, but outward normal was a positive x-axis, but the shear stress by itself points in the negative direction. So it is the minus tau xy that is there. So tau x prime y prime in this case is equals to minus tau xy. So let's write that as well, which is already written over here, right? So let's clarify that. So your tau x prime y prime becomes equals to minus of tau xy. Now which point is this on the Mohr circle? On the Mohr circle, we had already located this point A where theta was equals to 0. Now where in this Mohr circle, do we also have the tau xy becomes equals to minus tau x prime y prime, which is this particular point over here. Now at this particular point, your sigma x prime is equals to this one over here. So let's mark that. As we already saw, when we rotated by 90 degrees, this one was pointing towards the sigma x prime becomes equals to sigma y. So let's go ahead and mark that particular point there as well. So here in this case, you have your sigma x prime as equals to sigma y, and this is tau x prime y prime equals to tau x equals to minus of tau xy that you have over here, right? Now you may be asking this question that I have a minus tau xy here as well, so why was this point not equal to your the value of the sigma y that is there? It is not, because this particular point you have already have this sigma x over here, so that the value of that one is sigma x over that. At that particular point it is not equals to that minus minus tau xy that you have. If the value of the stress over there was equal to sigma x, so suppose you have sigma x, sigma y was also sigma x, then you may have had a general point over at this particular location over here, right? Now one extremely important thing to note is that you see this point G is diametrically opposite to A, right? Essentially that means that from here you had to have a rotation of 180 degrees in the original system, in the original element, to get from 0 to this one for x, where x prime in the previous page where coincidental is this 0 degree. To make it coincidental with the y axis, I had to rotate by 90 degrees, but here to locate the point that represents the state of stress for this rotated axis that is there, I had to go a 2 theta 180 degree. So what does that tell you? That tells you that a rotation theta in the original element leads to a rotation of 2 theta in the Mohr plane, right? So let's maybe make a note of that, and maybe this is noted later as well, but it's a good time to note this. So rotation So rotation of theta in the original element leads to a rotation of 2 theta in the Mohr circle that you have over here. Okay, so now with this we have for the original element itself, right? We have located the points which are there. So we have located the point where you have the point A, which represents your sigma x tau xy. We have located the point G over here where the value of the stress is sigma y, which is over here. Don't worry too much about the stress. Once you have located the point A, the state of stress, the others get automatically automatically drawn. The only reason why this is negative over here, because in this case your tau x prime y prime for the rotated axis points towards the negative y direction, which is over here. Okay, so let's go ahead and take a look at a few other things in the Mohr circle. This is what the first point is, what we just wrote. So this shows the two points which are there. So this one corresponds to the point A, where remember where x prime was coincidental with the x-axis, and this point corresponds to the point G where you have rotated this one to an angle of 90 degrees. So these are the very important points. A rotation theta in the physical plane corresponds to a rotation of 2 theta in the Mohr plane, right? And one more important thing, and this is the reason why your sigma points, if you look at different books, the sigma points positive to the positive in this direction and tau points positive to the right, the direction of the rotation remains the same. If you had taken the tau in the upward place, where you will see in some of the books they take the tau in the upward side, it becomes slightly a little less intuitive, because the direction of rotation also changes, and here we are preserving the direction direction of rotation. So the direction of rotation remains the same. So what is shown here is that an anti-clockwise rotation in the physical plane. See here, to go from theta equals to 0 to theta equals to 90 degree, you have to rotate the element in an anti-clockwise manner over here. Correspondingly, here the theta 90 become 2 theta equals to 180, but here also you had to go from here to here in an anti-clockwise manner, that is there to get to this point G over here. So an anti-clockwise rotation in the physical plane leads to an anti-clockwise rotation in the Mohr plane. You will see when we will solve some of the problems of finding the principal stresses or the maximum in plane shear, this will become extremely handy, where you don't have to always keep a track and think. You have to just mark the points in the Mohr circle, and then you will automatically get the points which is happening in the physical plane. So important takeaway is that the direction of rotation remains the same. So now that we have many things at our disposal, let's go ahead and do a summary of how to draw the Mohr circle and how to find the different points which are there, right? Okay, so this is the overall summary that you get. So first you establish, so this is the step 1, right? So we'll walk through all the steps from step 1 to step 6. So the first step is to establish the coordinate system, which we have already done, that sigma is positive to the right and tau is the positive downwards over here. Okay, so the next point is that since you have to draw a circle, right? So that is why for the circle you need to know where is the center of the circle. We have seen the center of the circle always happens at the average point, that is the sigma x plus sigma y by 2, where this was nothing but the sigma average, right? So once you have located the center C of this circle, then you first given this element. So usually if you remember all the problems we started with, we were given with, you know, this element over here, where the one face is perpendicular to the longitudinal axis, the other face is parallel to the longitudinal axis. So you first locate your reference point, that is the sigma x, and the tau xy, that is over here. So sigma x is here and tau xy over here. Now if you connect from the center to this point, this gives your radius of the circle R, and now that you have the center and the radius of the circle, you can go ahead and you can sketch the whole circle that is there. And note that this radius of the circle that is there, what it says in this step 5 is that is equals to this one. This is also what something we have derived. So once you know the center of the circle and the radius of the circle, you can sketch this entire circle that is there. Now let's go back and revisit the different salient points of the Mohr circle, that you know where your principal stresses are, where your other stresses which are over there. So let's go ahead and look at this exhaustive set of pointers about the Mohr circle, right? So let me turn off my camera because it will overlay with what is being shown over here. So let me go to this one. Okay, all right. So you see that first that you have over here, so this is your Mohr circle which you have already sort of established over here. Let's go through the different points which are there. Okay, so this is the original point A. So this is the original state of stress at the point A. This is the point A over here where theta was equals to 0. So this is marked already, right? Okay, and this has helped you to sketch the circle, what we saw in the previous step. You find the center of the circle, you find the point A, you join from the center to the point A with this R over here, and that gives you the the radius of the circle, and that essentially helps you to sketch the circle over here, right? Okay, so that takes care of the first part. Okay, let's take a look at the second part. The second part is that the principal stresses, which we have already seen. Principal stresses are nothing but the extreme right and the left end of the circle which is there. So sigma 1 and sigma 2, the coordinates of the point where the circle intersects the sigma axis, that is tau equals to 0. Remember, this was the element rotated about the principal plane where you had no tau. One was theta p1 and the other one was theta p2. Now here is the important bit. The important bit now is that how do we find the theta p1 and theta p2? So how do I find this? How do I find that how much angle I had to rotate to sigma 1 and how much angle I had to rotate to this one? Now remember, for this, that what we had discussed was that your rotation in the rotation theta in the original plane corresponds to a rotation of 2 theta in the Mohr plane, right? Okay, so now if we are starting with this point A over here and say this point B that you see, that is your sigma 1 that you have over here. Let me go ahead and maybe mark that. So if this is my let me turn my pen on. Yeah, if this point is my sigma 1 and this point is my sigma 2 that I have over here, you see that to get to the principal directions I have to rotate this element. So from A I am trying to reach this point B over here. So from here I have to go, what is the shortest way for me to reach from, you know, this point to this particular point over here? The shortest way for me to reach is this, is 2 theta p1. So this angle I am going to go from here, point A to point B, and this is called 2 theta p1 because the rotation theta in the original plane corresponds to 2 theta. So if this is 2 theta p1, the rotation in the original plane is just the theta p1 that you have over here. So this is the theta p1 that you have over here. Now to get to this point D over, now you really don't need to calculate, you know, this point over here, because this point you can just do 90 degrees plus that one over here, or if you want to go from here all the way to this one, to this particular point, if you divide by 2, that will give you this particular point over here. Now you might also want to go from here in the clockwise direction over here. What this angle will give you, can you understand what this angle is going to give you? You're going in the clockwise direction. This is essentially this angle over here. This is essentially this angle, which is same as, you know, the sense of the stress, and since it's a rectangular element, it will eventually give you the similar number that you have over here. So this is the remaining angle, if you want to call that the remaining angle that you get over. So either way you go, you will eventually end up with the same diagram for the rotated axis that is there. Okay, so I hope that is clear how we got 2 theta p1 corresponds to theta p1 over here. Now let's go to the next point. Now I need to turn off my webcam, so let's go to the next point. So the next point is that that the maximum shear, where, you know, these 2 points over here, right? Now for this maximum shear, you see from here I had to go to this, you know, clockwise rotation of 2 theta s1. Why 2 theta? Because in the original plane it will be theta. So these are the points of the absolute shear that you have. So tau x prime y prime, maximum in plane shear. And remember, at these points the value of the shear stress is the sigma average that you see. So sigma average and the maximum coordinates are your E and F that you see over here, and the direction of rotation is the same. Here it is clockwise. In different problems it will be different. We'll look at some problem examples, then you will see. And the last thing is that, suppose instead of asking you to find the maximum, you know, principal stresses or the maximum in plane shear, I ask you to calculate the state of stress at any general point, you know, P, right? So here this point P is at an angle of, you know, some 2 theta in the Mohr plane, so that means at a theta in the original plane. So if you're given the original element for this particular point P as well, from the properties of the circle you can calculate what is going to be the state of stress of this particular. You can calculate the sigma x prime for this one, diametrically opposite will be sigma y prime, and tau x prime y prime for the rotated element that is there, right? Okay, lot of things I know, so you must be tired with all of, you know, these discussions over here, but trust me, it is conceptually very simple. This is a good textbook if you want to refer more on the Mohr circle discussions that is there. So now all that we have learned, so many different aspects of the Mohr circle, it might appear complicated in the beginning, but trust me, these graphical techniques are much easier than remembering the equations, and I will show you that how easy Mohr circle makes your life by solving a couple of problems where you will appreciate, and then for the other problems you would only want to do Mohr circle and not remember any of the other equations that you said. So let's go ahead and take a look at a couple of example problems.